Welcome friends to this NPTEL online certification course of environmental soil chemistry, and today we are going to start week 5 or module 5, and in this week we will be basically discussing about ion exchange process and several aspects of ion exchange phenomena. So, these are the topics or concepts which we are going to cover in this week. First of all, we are going to cover the ion exchange capacity, then we are going to cover what is cation exchange capacity or CEC. Then we will be considering we will be focusing on the methods of cation exchange capacity determination, then characteristics of ion exchange, percent base saturation. We will be also learning about the cation exchange equilibrium constants, then selectivity coefficients, and finally we will be seeing the thermodynamics of ion exchange. So, what is ion exchange? Ion exchange is basically, it is a very important process as far as the soil chemistry is concerned. This ion exchange basically governs several aspects of soil, soil fertility and soil biological activities. Several things have been are governed by this ion exchange process. So, this ion exchange can be defined as the interchange between an ion in solution and another ion in the boundary layer between the solution and a charged surface. So, source of cation exchange in soils are basically clay minerals, organic matter and amorphous minerals. If you remember, we have already discussed that how these clay minerals and amorphous minerals and organic minerals governed basically the chemical the soil chemical process due to the charge development. All these ion exchange processes are dependent on charge development, which cannot be seen in case of sand and silt particles. However, in case of soil clay, we can see that negative charge, the soil, in case of soil clay, it can develop negative charge by either permanent charge or through variable charge. Variable charge is also known as the pH dependent charge, which depends on the pH of the surrounding solution, whereas in case of permanent charge it based on the isomorphous substitution of the clay minerals. And amorphous minerals are also important for charge development, because these iron oxides and aluminum oxides and hydroxides are basically developing this pH dependent charge, and most of the charge which develops in the organic matter are pH dependent charge, and organic matter produces couple of fold higher negative charge than that of clay minerals. So, the sources of cation exchange are basically these charge which develops in the clay minerals, amorphous minerals and organic matter. Now, sources of anion exchange in the soil. So, obviously, this clay mineral develop the negative charge, organic matter develops negative charge, amorphous mineral develop negative charge in the alkaline condition. So, in this, these are the negative charge which are responsible for cation exchange in soil. Now, the opposite of cation exchange is called the anion exchange. Now, sources of anion exchange is again clay minerals, because for example, in case of kaolinite, it shows high pH dependent, it is basically showing whatever charge it develops basically pH dependent charge, and this pH dependent charge can be positive depending on the surrounding solution pH. In case of acidic medium, it can develop positive charge, and also primarily 1:1 type of clay such as kaolinite, metal oxides and amorphous mineral, they can develop positive charge, and these positive charge can attract these negatively charged anions in the soils. So, cation exchange capacity basically develops due to clay minerals, organic matter and amorphous minerals. In case of anion exchange capacity, it basically is a resultant from clay minerals, primarily 1:1 type of clay such as kaolinite and metal oxides and amorphous mineral like allophane. Now, the ion exchange capacity is the maximum adsorption of readily exchangeable ion on soil particle surfaces. Now, ion exchange capacity can be ion exchange capacity is basically a summation of both cation exchange capacity as well as anion exchange capacity. Cation exchange capacity is the total capacity of the soil to hold exchangeable cations. However, anion exchange capacity, which is the sum of the total exchangeable anions that a soil can adsorb. So, again Ion exchange capacity is basically a broader term which encompasses both cation exchange capacity and anion exchange capacity. Cation exchange capacity is the total capacity of a soil to hold exchangeable cations, whereas the anion exchange capacity is the sum of the total exchangeable anions that a soil can absorb. So, the magnitude of cation exchange capacity in soil is usually greater than anion exchange capacity, because permanent charge is always higher than that of variable charge. So, soil lacking the ability to retain anions, that can show lower anion exchange capacity. So, you may ask that, okay, if the soil has lower anion exchange capacity, what is the problem in that? The problem is there are certain minerals which are available to the plant in terms of negative anions. So, for example, sulphate, phosphate. So, the sulphate can readily leach away and is no longer available to support the plant growth if the soil is lacking the ability to retain the anions. So, soil needs to have both cation exchange capacity and anion exchange capacity to supply both cations and anionic nutrients to the plants. So, this picture, this picture basically shows the two different condition. In one condition, you can see a high development of negative charge in the clay surface, and obviously the bounded cations are also higher in case of this condition, condition A, and in case of condition B, you can see the development of negative charge is very less. As a result of that, the attachment of positive charge counter ions are also very less. So, basically it is clear that in case of condition A, the cation exchange capacity is higher as compared to the condition B. So, CEC of soil A is higher than CEC of soil B. So, the CEC or catenation capacity of a soil is a measure of the quantity of negatively charged site on soil surfaces that can retain positively charged ions or cations. Okay, such as calcium. Generally, these cations are calcium, magnesium, potassium, and these are basically attracted to the negatively charged clay surface by electrostatic forces. These electrostatic forces are so the electrostatic forces are the major binding force between the cations as well as the negatively charged clay surface. Now, cations can retain electrostatically, which are retained electrostatically are easily exchangeable with cations in the soil solution. So, a soil with a higher cation exchange capacity has a greater capacity to maintain adequate quantities of calcium, magnesium and potassium than a soil with a low CEC. Obviously, when the soil has the higher capacity to retain more cationic nutrients, it has also greater capacity to maintain adequate quantities of calcium, magnesium, potassium than a soil with a lower CEC. So, a soil with a higher CEC may not, this is a there is a condition. So, a soil with a higher CEC may not necessarily be more fertile, because of the soil CEC can also be occupied by acidic cations such as hydrogen and aluminum. Now, these hydrogen and aluminum are not very beneficial to the plant. For example, aluminum in the acidic soil, when the pH goes below 5, this aluminum concentration increases, and when the aluminum concentration increases, it basically interferes with the root growth and it kills the plant. So, this L3 plus, although it is a cation, it is not beneficial for the plant. So, and also H plus ion, increase in the H plus ion also increase the acidity of the soil, which is not beneficial for the plant growth. So, or for soil fertility. So, if the soil has higher CEC, that may not necessarily be more fertile, because there may be presence of this H plus ion, aluminum ion. However, when combined with other measures of soil fertility, then CEC can be considered as a good indicator of soil quality and productivity. Generally, if a soil has high CEC, then we can consider that soil has a high soil quality or productivity. Now, cation exchange sites are found primarily on clay minerals and organic matter surfaces, because clay mineral develops this permanent permanent charge due to isomorphous substitution. And in case of organic matter also, these these aromatic functional groups, aromatic aliphatic functional groups like carboxylic, like carboxyl function group, then phenolic groups, they basically dissociate to form the negative charge on the organic matter surface, and as a result they can attract positively charged cations. So, soil organic matter will develop a greater CEC at near neutral pH than under acidic condition because of pH dependent CEC. At acidic condition, positive charge development in case of variable charge surface. So, obviously, near neutral condition organic matter will develop greater CEC because there will be more negative charge. In case of acidic condition, there will be positive charge, there is a possibility of positive charge development. So, addition of organic matter will likely increase soil cationation capacity over time, and on the other hand a soil cationation capacity can decrease with time as well through natural or fertilizer induced acidification and organic matter decomposition. So, soil CAC also can decrease with time through natural fertilizer induced acidification. There are some fertilizer which are acid forming fertilizers. So, when you apply this fertilizer into the soil, they form acidic reaction and the soil become acidic. So, the CEC can decrease in that condition. So, soil CEC is normally expressed in one of two numerically equivalent sets of units. Either you can express, so earlier people used to express this cationation capacity in terms of milliequivalent of charge per milliequivalent charge per 100 grams of dry soil. Nowadays, we generally use the C mol C per kg, that is centimoles of charge per kilogram of dry soil to express this cationation capacity. So, these two are the generally used units of cationation capacity. Now, what are the methods of determining the cationation capacity? So, for soil classification purpose, a soil cationation capacity often measures at a standard pH value. So, examples are, for example, generally we use ammonium acetate method following these Schoenberger and Reibelbe's method of 1930, which is buffered at pH 7, and also barium chloride and triethanolamine method of Mehlich, which is buffered at pH 8.2. So, basically we use two different solution, one at pH 7. So, it is buffered at pH 7, another method we use the barium chloride and triethanolamine method, so which is buffered at pH 8.2. So, buffer CEC method, why it is important and what is their drawback? So, buffer CEC method, the buffer solution basically we apply to the soil. So, if the pH of the buffer is more than the pH of the native soil, then this method measures not only the cation sites active at the pH of the particular soil, but also pH dependent exchange site that would become negatively charged if the soil pH were raised to 7 or 8.2. So, here you see two different when you add two different reagents, one is buffered at pH 7, another is buffered at pH 8.2. So, if the native soil has a pH dependent charge and its pH is less than 7 or 8.2, when you add this buffer, they will, due to this negative charge surface, due to this variable charge, they will develop negative charge. So, the CEC which can be measured by using this method can exaggregate the true CEC of the acid soils. So, the acid soil generally have the lower pH than 7 and 8.2, and in this acid soil when you apply these two buffer solution, they will basically increase the negatively charged surface due to the pH dependence, and as a result the CEC will be exaggregated. So, the buffered method, that is ammonium at pH 7 or barium at pH 8.2, measures the potential or maximum cationation capacity of a soil. So, we can see that when we are using the buffer method in the laboratory, it is basically giving us the potential or maximum catenation capacity of the soil. Another method is called the unbuffered method. So, unbuffered method can give us the effective catenation capacity. So, the unbuffered method can measure only the effective catenation capacity in the soil, and this method gives result when the pH of the native soil is lower than that of buffer pH. So, again we can see that there are two methods, one is buffer method and unbuffered method. Buffer method use the pH of 7 in case of sodium ammonium acetate, and in case of barium, in case of barium chloride and triethanolamine mixture, it uses the buffer of basically 8.2, and when we add this buffer into the acidic solution, due to the variable charge surface, this variable charge surface can turn into negative charge by increasing the pH while adding this buffer, and as a result they will have more catenation capacity, and as a result this buffer method can show exaggregate CEC. So, effective CEC you have to use the unbuffered method. So, let us see two widely used methods for determining the catenation capacity. The first method is distillation method of or ammonium saturation method, where we are using the 1 neutral normal ammonium acetate at pH 7, and another method is called centrifugal method with the sodium saturation method, where we are using 1 normal sodium ammonium acetate, one normal sodium acetate with a pH of 8.2. So, these two methods are widely used methods for determining the catenation capacity. However, we will be discussing the distillation methods in details later on. So, what are the basic steps? The idea shows the steps for determining the CEC is basically the soil is leached with ammonium soil solution. So, if you can see, this is for example, this is a funnel, and in this funnel we are packing the soil which contains basically calcium, magnesium, potassium and H plus and Al3 plus ions. So, when we are leaching the soil with this ammonium acetate or ammonium salt solution, this ammonium basically replaces all the cations which comes into the leachate. Okay. So, after removing the excess of ammonium salt solution, soil is further again leached with potassium solution. So, in the first step we are basically leaching the soil cations using the ammonium solution. In the second step we are basically leaching the ammonium solution with the ammonium adsorbed soil with the K plus solution, okay, and this with this K plus solution or potassium solution, which basically replaces this ammonium. So, finally, what we get? So, ammonium washed into the lower container, and the concentration of the ammonium will be determined with the CEC of the soil. So, this is 2 to 3 step process. First step, we are leaching the soil with the ammonium solution, and all the ammonium get adsorbed by replacing all the cations, and in the second step we are basically leaching this ammonium saturated soil with the potassium solution, so that all the ammonium get leached down and this saturated by potassium. So, let us see one calculation based on that. So, calculate based on that. So, after leaching, let us assume that after leaching a soil with 0.4 liter of ammonium solution, let us consider that we have used only 0.4 liter of ammonium acetate solution. All the exchangeable cations shown in the soil samples were displaced off the colloid and washed into the beaker along with the excess of ammonium ions. Now, the solution in this beaker was analyzed for calcium, magnesium, potassium, aluminum and H with the following results. So, we got for calcium 200 ppm of calcium, 60 ppm of magnesium ions, 97 ppm of K plus ion, 5 ppm of H plus ion and 67.5 ppm of Al3 plus ions. So, because only we have used 0.4 liter of solution was collected from the soil sample and the soil sample weighted only 0.1 kg or 100 grams. These results can be multiplied with 0.4 and 10 to give the amounts of each ion collected in ppm or mg per kg in soil. So, basically we have to multiply it with 0.4 and 10 to convert into the milligram per kg or ppm. So, as an example we can show the calculation for the calcium. So, let us consider this calcium. We have measured the calcium in the leachate and which comes around 200 milligram per liter. So, if we see it is a 200 milligram calcium per liter. So, basically we are multiplying it with 0.4 liter and then we are multiplying it with the 10 grams to get ultimately milligram per kg. So, ultimately we are getting 800 milligram of calcium per kg of soil. Now, how to convert it to CEC? Now, for calcium we know the atomic weight is approximately 40 gram per mole. So, 1 mole of calcium contains 40 grams. So, we could calculate the centimole of exchangeable calcium ions in 1 kg of soil. So, we already know that we have 800 milligram of calcium ions per kg of soil. So, if we convert it to centimole by considering 1 mole is equivalent to 40 grams. So, basically we are multiplying it 1 gram by 1000 mg. So, it can convert it to mg and then 1 mole by 40 grams we know that and then we can convert into centimole. So, ultimately by simplification we can get this 800 mg of calcium ions per kg of soil can be represented by 2 mole calcium ions per kg of soil. Okay. So, now, repeating this calculation for each element provides the following results. So, we can get 2 centimole of calcium ions per kg of soil, 1 centimole of magnesium ions per kg of soil, 1 centimole of K plus ion per kg of soil, 2 centimole of protons or H plus ion per kg of soil and 1 centimole of Al3 plus per kg of soil. Now, we must multiply the centimole per kg of each element by the corresponding valency of the ion to convert it to centimole of charge. So, when we multiply the centimole with the corresponding charge, we get centimole of charge. So, C mole C, which is the ultimate C mole C per kg, so which is the ultimate unit of catenation capacity. So, basically using the Ca2, let us consider the Ca2 as an example again. So, basically we got 800 mg per kg, 800 mg calcium per kg of soil. From that we calculated it is basically 2 centimole of calcium per kg of soil. So, then we multiply it with the 2 centimole C from calcium per centimole of calcium. So, 1 centimole of calcium basically contain 2 centimole charge from calcium. So, because it is valency of 2. So, we get ultimately 4 centimole charge from calcium per kg of soil. So, for calcium ultimately we get 4 centimole charge from calcium per kg of soil. So, repeating this calculation provides the following results: 4 centimole charge of calcium per kg of soil, 2 centimole charge of magnesium per kg of soil, 1 centimole charge of potassium per kg of soil, 2 centimole charge of H plus per kg of soil and 3 centimole charge of Al3 plus per kg of soil. Now, assuming the 5 elements measured account for nearly all the exchangeable cations, the sum of their charges, that is 4 plus 2 plus 1 plus 2 plus 3, that is 12, equals to the total CEC or catenation capacity of the soil, that is 12 centimole of charge per kg of soil. So, this is how we can calculate the catenation capacity. So, summarily we have started with a particular cation. we converted that particular, we have calculated, if we just go back a little bit. So, we have started with the concentration of the analyzed leachate, and then basically we converted into milligram per kg depending on whatever amount of solution we have taken and what is the weight of the initial weight of the soil. So, from there we can convert into milligram per kg. Once we convert it to milligram per kg, the next step is to convert into the centimole per kg. Once we convert it to centimole per kg, the next step is to convert into centimole charge per kg of soil. So, we can convert these for each and every cations which are present into the solution, and once we do that, it is basically the summation of all the centimolar charge to calculate the total CEC of the soil. So, this is one of the approach of calculating based on the laboratory data of CEC. Another approach, the second method, is measuring the amount of ammonium plus. Now, you know that I have shown you that when we are using excess of K plus ion to leach whatever ammonium which was adsorbed onto the clay surface, that ammonium can be further leached, and these ammonium concentration in the leachate can be measured. So, assume that the ammonium concentration in the beaker D, that is the last beaker, to be 540 milligram of ammonium per liter. So, as in method 1, because only 0.4 liter of solution was collected from the soil sample and the soil sample weighted around 100 grams or 0.1 kg, these results can be calculated as following to give the amount of ammonium ions collected in mg per kg. So, similarly, in the previous example we have calculated it based on individual cation. Here we are considering the ammonium cations, and then using the ammonium cation we have calculated this, that is 2160 milligram of ammonium per kg of soil. Now, if we convert this 2160 milligram per kg of soil ammonium to the centimole, to the centimole, so basically we will get 12 centimole of ammonium per kg of soil, and since ammonium valence is 1. So, obviously, the centimole charge will be also the same. So, basically the answer is here 12 centimole charge per kg of soil. So, the CEC is basically the 12 centimole charge per kg of soil. So, this is how we can calculate the CEC. Again, CEC to basically if we just recap whatever we have covered. So, CEC is again the cation exchange capacity. It is basically the capacity of a soil to exchange its adsorbed cation to the cations in the surrounding solution. Cation exchange capacity basically is an indicator of the soil fertility. Although sometime it may be misleading because of the presence of H plus ion and L3 plus ion which are not suitable for the plant growth. And anion exchange capacity is just opposite to the cation exchange capacity. In the soil, cation exchange capacity generally develops due to the presence of the permanent charge as well as the organic matter, as well as the positive as well as the negative charge, negative variable charge in the amorphous clay mineral. However, the anion exchange capacity generally develops from the 1:1 type of mineral like kaolinite as well as amorphous mineral, and basically these are the minerals which produces the variable charge, and from there we can calculate the anion exchange capacity. Now, cation exchange capacity can be measured by both buffered method and unbuffered method. In the buffered method, we use the ammonium acetate with a buffer pH of 7, and basically these ammonium acetate these ammonium ions from this solution basically replace all the cations, and then we can measure the cation exchange capacity either by measuring the individual cations or by measuring the ammoniums which are further leached by another solution called potassium enriched solution. So, this is how we can calculate the cation exchange capacity by two different methods. Okay. So, So, I told you that another the most widely used method in the soil in the laboratory uh, is the distillation method or ammonium saturation method. So, what is the principle of this distillation method? So, the principle of this distillation method, in this method the CEC of the soil is measured by leaching with neutral 1 normal ammonium acetate, just like we have seen, and this results saturation of the exchange complex with ammonium ions. We know that. Then these adsorbed ammonium ions are determined by distillation of the soil. So, in this step we are basically these adsorbed ammonium ions are determined by distillation of the soil with magnesia, that is MgO. Now, the ultimately ammonia gas will evolve during the process, which is basically absorbed in known amount of acids, which is taken in excess amount, and then the unreacted acid is back titrated with the standard alkali. So, here again we take the soil and then we saturate it with the neutral normal ammonium acetate. Ammonium replace all the cations, and these ammonium can be further in the presence of magnesium oxide. This ammonium produces the ammonia, which is basically absorbed in the excess amount of a standard acid, and whatever acid is remaining unreacted can be back titrated with the standard alkali, and from there we can calculate what is the generation of the ammonia, and this from this generated ammonia we can calculate the CEC. So, the reaction which is involved in this distillation method is basically we start with the ammonium acetate, which is dissociated into ammonium and acetate ions. So, if the soil has a particular cation, so this ammonium basically replace that cation and produce and saturating the soil with ammonium. Now, in the next step, this magnesium oxide in the presence of water produces magnesium ions as well as 2 hydroxyl anions, and this ammonium saturated soil in the presence of these magnesium ions as well as 2 hydroxyl ions can produce this ammonia gas as well as magnesium saturated soil and water. So, these ammonium get absorbed into the some acid solution, and whatever acid is remaining unreacted after this absorption of ammonia can be back titrated with the standard alkali. So, this is how in the laboratory using the distillation method we generally measure the catenation capacity of the soil. So, guys, I hope that you have learned some basic overview of ion exchange process and catenation capacity and anion exchange capacity, how we measured catenation capacity, how to calculate catenation capacity. So, let us meet in our next lecture to discuss more on the ion exchange phenomena and how it changes and what are the implications of ion exchange process in the soil. Thank you very much.